So in the previous video, we began this discussion of sugars having an intramolecular reaction with themselves and talking about the possibility of the very first carbon that has the aldehyde group or ketone group to come around and basically hook up with the number 5 carbon in a 6 carbon chain sugar, right? So we did this example of glucose. We started off with glucose. We can never draw glucose too many times, right? We'll keep drawing it until we get comfortable with it. So here's 4 carbons in the center, and this is right and left and right and right. Okay, so this is the structure of glucose, and we said that this aldehyde group is making this carbon partially positive. And then what will bring the magic here is at carbon number 5, this oxygen will be element number 6 in the ring. So we can see a hookup that happens between the first carbon with the aldehyde group on it and then this oxygen, which is on the 5th carbon. However, the oxygen makes the 6th atom in the ring. Again, this is the first one in the ring, second one in the ring, third one in the ring, fourth one in the ring, fifth one in the ring, and this would be the 6th atom that makes the ring up. So we see this carbon, and then here's carbon 2, carbon 3, carbon 4, carbon 5, that has an oxygen on it that will do the hookup. And look, this is 6 elements, right? 1, 2, 3, 4, 5, 6. 6 atoms in that ring. And that's what we want to see. That gives us some stability there. So there's a 6 carbon, we can't forget about that, that has a CH2OH group on it. Okay, so there is our 6th carbon, and this is our OH group off of that 6th carbon. Now that's kind of where we stopped. Now there's some definitions that we need to talk about here with this structure. So we said that this was the Haworth projection. That's what we formally call that structure. Something else that we need to talk about is this carbon here. This carbon is very special. And the reason that we call it special is because this was a carbon that's double bonded to an oxygen. But what will happen is that that double bond O will break. So this did have a double bond O on it. However, the double bond breaks to make room for this new bond that's formed with that what was a OH group. Okay, so we got to free up one of those bonds. So we got to make this oxygen happy. And the way that we make that oxygen happy is that we give it a hydrogen. And now everything is okay. And you know, the carbohydrate structure, it's okay with these OH groups, of course, because it has OH groups everywhere. Notice that we left out the OH groups on these other carbons. They are on here. We've not drawn them yet, but they're there. I want to place a focus on that very first carbon, however. The very first carbon's special. And because it's so special, we have a special term for it. And this special term is called an anomeric carbon. So if you run across a question that talks about the anomeric carbon, that is the anomeric carbon of the sugar. It's the carbon that's connected to the oxygen of the ring. Okay, so this is the carbon connected to the oxygen of the ring. Now, this carbon's connected to an oxygen, this carbon's connected to the oxygen, this carbon's connected to an oxygen, this carbon's connected to an oxygen, this carbon's connected to the oxygen, but this carbon in particular, that is where my aldehyde group was. That's where the double bond O group was. That double bond O has gotten destroyed and a new bond has formed to that carbon. And that, by definition, is an anomeric carbon. Now, anomeric carbons are going to give us something called anomers. So we've got to discuss what an anomer is. Now, if you're careful on the wording, anomer sounds awfully like enantiomer, right? An enantiomer was the R and S form or the D and L form of these sugars or these chiral carbons. And here we have an anomer. It sounds almost identical to an enantiomer, right? Okay, so we've got to discuss what an anomer is. And an anomer is basically two sugars that differ in configuration only at the carbonyl carbon. Okay, so this was our carbonyl carbon. And that is the reason, one of the reasons, that we call that the anomeric carbon, because that is where our anomer is going to be structured. Now, what is this whole concept of an anomer? Is it something that's going to be complicated? Is it something that I need to worry my time with? Well, yeah, we need to worry our time with it because it is slightly important. So what we're going to find out is that this carbon that's involved in this six-membered sugar ring can take on two forms. And the form that it takes on is very similar to what we've always seen before in the past. Is the OH group to the left or is it to the right? Right? That's what distinguishes between D and L sugars. Well, this anomeric carbon, that is where the aldehyde group was. That's where that carbonyl bond was. Whether it's an aldehyde or ketone doesn't really matter. That's where the double bond O was. And this carbon could form an OH group that points down, or its OH group could point up on the ring. Can't really talk about left and right here. Left and right was due to the skeleton backbone of the Fischer projection. We could concern ourselves with left hand and right hand of the molecule. Here we got to take a different perspective. Here we've got to look at basically, is it toward the top or is it toward the bottom of the molecule? So we call that location up and down, or at least I do. So in the first round, I could maybe put OH that points below the molecule if you want to look at it that way. And then in the second one, I'll put the OH group above the molecule if you want to look at it that way. So these two locations are very important, and it's as important as D's and L's are back in the day, back in those videos when we first introduced carbohydrates. So we've got a certain way that we denote which direction this OH group is in. If the OH points down, like in this case here, if the OH group points down, then this term is going to be called the alpha anomer. And if we have the OH group that points up, this term is going to be called the beta anomer. Now, this started all with glucose. That's the structure that we started with up here at the top. This was D-glucose, right? So that means that if glucose makes a ring structure, this would kind of be like alpha glucose, and we would call this beta glucose. Now, I can extend that on even further if I wanted to. This glucose, we can call it glucose here, is the D form because this OH group is to the right-hand side. Okay, so that's D-glucose. If I kept all of the locations of the OH groups the same when I made these ring structures, well, there's a difference here when the ring structure is made. If the OH points down, we would call this alpha D glucose, and if the OH group points up, we would call this beta D glucose. Okay, so very important that you know what alpha and beta mean. Now, what we're leaving off here are where are the other OH groups, right? These or this glucose has an OH group on every single carbon of the chain. And it should have an OH group as well on every single carbon in the ring. That's something that I've not done and I've not labeled yet because I don't want us to take that far of a step or do too many things at one time. What I want you to focus on right now is the whole concept that these straight chain sugars can make rings. And when they make a ring, they can basically hook up with an intramolecular reaction between the carbonyl and the hydroxide of the molecule. When they hook up and they join, there is a possibility, an option for this carbon. And that carbon can choose to point its OH group down, or it can choose to point its OH group up. And depending on that direction, that's where we get these terms of alpha sugars and beta sugars. So alpha glucose, beta glucose. We sandwiched the D in there just because we knew a little bit more information about it. We knew that this was the D version of the glucose itself. Okay, so in the next video, we're finally going to take the next step, building up here, and we want to take a look at how we assign the direction of the other OH groups themselves. So where do the other OH groups go? So for instance, I need to make a relationship between this OH group that's on the right-hand side and how I need to draw that here in this structure. Now there's something I forgot here. This needs to be a CH2OH and this needs to be a CH2OH. But I need to start making the correspondence between, okay, the OH group is on the right here. So does that mean in the structure, does it go up or does it go down? So in this third carbon, there's an OH there, it's on the left. So in the ring, does that mean it goes up or does that mean it goes down? So that's what we're going to focus on in the next video. We're not going to take away from the Haworth projection just yet. We're still getting a little deeper into it, so be patient. We're almost finished with the Haworth.